So, I believe this is your last day of this camp, right? Okay, so you are very happy that this is last day. Okay, so how was it? Did you enjoy?
Yes.
How was the ambience? Okay, good. All right, so I am told that in this last session, I show some of my small experiments which I had been working on for quite some time, right. So, I have some of them here. The basic idea is to connect what we teach, what we study in schools, colleges with the practical situations, something which is not in terms of alpha, beta, gamma, Young's modulus, y and this and that, but some phenomena which actually takes place. So, many times there is a lot of gap between what we understand from our equations and what actually goes on. So, that is why these experiments are very important. And since I am a physics professor, you know about me, right? Or should I introduce myself? Since I am a physics professor, therefore, my entire this effort is towards science education, but engineering education is surely a related thing. So, many times I take escape through this engineering route. If someone asks some question that can we do this, can we do that, I say that this is engineering problem, this is not physics problem. So, physics will tell that what can be done, what cannot be done based on the theories, but whether it is feasible, whether it is useful, that is a engineering problem. And if that engineering competence is not there, if we do not make products out of theories, then those theories are also not of much use, right. So, that is the complementary role. We understand the theories, we understand the phenomena deeply, and then we know our society, we know our needs, we know our problems, and then we have this engineering competence, so that we can actually tune the things and come out with useful workable things which are financially and so on, so on. So, that is the kind of relation between science and engineering. So, that is the background. So, I will not give a lot of background and speech, and will directly go for some experiments. Okay. So, who is sleeping? Anyone sleeping here? No? Okay, very good. Can you volunteer? Okay, please come. Okay, this is a nice bag. Very nice bag, but quite light. There is nothing inside the bag? It's so light?
This one.
Okay, only one this. So, the bag is important, not the content inside the bag. All right. So, I will use my bag then, though it is very lousy. Okay. Now, first question, estimate how much will be the mass of this rod or pipe? 100 kilograms?
Grams.
100 grams?
Yeah, 150 grams.
150 grams. And this one? Around
2 kg.
2 kg. Minus 150 grams will be okay? No. 1.85 kg, will you be happy with that?
Yeah, around 2 kg.
Right, around 2 kg. So, putting this together, if I say this is 2 kg, will it be fine?
Yeah.
We are making estimates, approximates, right. So, 2 kg. So, this whole thing is 2 kg. Now, tell me with what force earth is attracting this pipe bag system? With what force the earth is attracting this pipe bag system? The total mass is 2 kg. F equal to ma, okay, good. F equal to ma,
A equal to G.
A equal to G. Mental mathematics. Doing mathematics without pen. Yeah, go ahead.
And M is 2
M is 2
and
and G is 9.8
meter
meter per second
square.
square.
It will be
It will be
around 20
around 20,
Newton.
around 20 newtons. Wonderful. You have done a good job. Okay. Now, can you hold it in your hand, keeping this pipe horizontal?
Yeah.
Okay. Just one hand. Now, tell me how much force you are exerting on the pipe.
More than 2 kg.
More than 2 kg. Force is not in kg.
Newton.
2 newtons.
More than 2 Newton.
More than 2 newtons.
Around 20 Newtons.
Around 20 newtons. Okay. So, you are exerting a force of 20. In which direction? He is exerting force on the pipe. The magnitude is 20 newtons. Which direction?
Upward.
Upward. All right. Why do you say that? Why do you say that it is upward? Why do you say that it is 20 newtons?
Because the gravitation is pulling it down, and we are force is acting opposite to it.
So, Newton's third law. Okay. The earth is attracting this bag with 20 newtons, and he is applying, therefore, according to Newton's third law, he should apply 20 Newton upward. Right? How come? Okay, wait. Okay. I'll come to you. See, what is Newton's third law? Newton's third law says that, what does it say? Okay, so here which is the action? In this case, the earth is attracting it down with 20 newtons and he is pushing it up with 20 newtons. So, what is action here and what is reaction? We are using Newton's third law. So, there should be an action, there should be a reaction, they should have equal magnitude, they should have opposite directions. So, where is the action? Earth attracts bag. Earth attracts bag. What should be the reaction of this? Bag. Earth attracts earth. That should be the reaction. So, this bag should attract earth by 20 Newton in upward direction. Newton's law third law guarantees that. But Newton's third law will not impose anything on what is your name? Suchitra. Suchet Kumar. Okay. So, the Newton's third law will not impose any restriction on Suchet. He can apply 100 newtons, he can apply 1 newton, he can apply 20 newtons, 10 newtons. Newton's third law has nothing to do that. Okay. Earth is attracting the bag with 20 newtons downward, the bag is attracting earth 20 newtons upward. That must be ensured, Newton's third law, otherwise Newton's spirit will be in trouble. Okay. So, then how do you say, why do you say that he is applying 20 newtons upward? Newton's third law has not is not saying anything about this.
Second equation, so forces must be in equilibrium. So since downward force is 20, so some force in opposite direction 20 must be applied to keep it at that place.
All right. So, you are using Newton's second law, okay, or first law. Since it is static, net resultant force should be 0, and therefore, if the downward force is 20 Newton by earth on the bag, there must be an upward 20 Newton on the bag. Someone has to apply that, so that it remains static. So, the total is 0, and hence that upward force is 20 Newton upward, right? What is your name?
Jigesh Yadav.
Jigesh. You have given a wonderful answer, very nice. So, now you understand the logic of this?
Yeah.
Why you are applying 20, how do I ensure that you are applying 20 newtons? Since it is not moving, since it is not accelerated, since it is at rest in static position, the net total resultant force on this should be 0. Earth is already pulling it down 20 newtons, therefore, you must push it up 20 newtons, so that the total force becomes 0 and it remains stationary, right? Right, right. So, let me recap. How much is the mass? With what force the earth is attracting this? So, keep it at rest, how much force one should apply in upward direction? Right? Please hold it and keep it horizontal. Oh, you have to apply only 20 newtons. Come on, come on, come on. You have to apply only 20 newtons. What happened? Actually, yeah, actually. Tell me, where is the flaw in Jigesh logic? Is the mass increased? Is the force by the earth increased? Does am I going to non-inertial frame? So Newton's first law is still valid. So the resultant force must be 0. So if the downward force is 20 Newton, upward force must be 20 Newton. So you have to apply only 20 Newton. So what is so fuss about this? Apply only 20 newtons.
Actually, distance
Apply.
is increasing.
Fine, fine, fine. But Newton's law doesn't talk of distances. Newton's first law does not talk of distances. Opposite direction, upward. Earth is pulling downward. He should apply force upward. Earth is pulling by 20 newtons. He should also push by 20 newtons. You only have to apply 20 newtons to keep it stationary. Not more than that. So, what is the problem? Please hold it. You can apply 20 newtons. Okay, you have taken enough food today. You can apply 20 newtons. You are applying 20 newtons, right?
Yeah.
Okay, keep applying 20 newtons. Come on, keep applying 20 newtons. Jigesh, what happened? Why he is not able to hold it? Why he is not able to apply 20 newtons? Who applies? But why inclination? I have given him a horizontal rod. He could not hold it this way. He only needed to apply 20 newtons to keep it at rest. Why it should go down?
That is not applying on the center of the mass.
Fine. So Newton's law, first law doesn't say that. First law, second law, whatever. Okay, it doesn't say that. It says that if the total resultant force is 0, then and then only it can remain at rest. That is your Newton's law, first or second. From second also you can come to this conclusion, and first is exclusively separately written for the situations of rest or moving with uniform velocity. So whichever first or second, whichever you say, he has to apply only 20 newtons, not 21 newtons. Whether it is at center of mass, whether it is at corner or here or there. Okay. Can you guess how much force you did apply? Okay, let me help you. I'll put it here. Hold it, one hand. Hold it. Oh, come on. This is your place. I will shift. You are holding it, right?
Yeah.
Very difficult,
Yeah.
but still holding. Can you guess how much force you applied? Hold it here. Now you are applying 20 newtons.
Yeah.
Okay, you are applying 20 newtons. Now guess how much you are applying now?
30 kilogram meter per second.
30 newtons.
30 newtons.
Okay, and now
More than 30.
40? 40?
Maybe 40.
Maybe 40. Okay. Now, when he was applying 30 newtons, Newton's second law, he was applying 13. He was able to keep it at rest, right? It was very difficult for him to hold it, but you succeeded in keeping it at rest. Is that okay? At 30 newtons? So now, how can Newton rest in peace? He is applying 30 newtons on this pipe bag system. Earth is applying only 20 newtons. So there is a resultant force of 10 newtons upward, and still the system is at rest. What happened to Newton's second law? Why F is not equal to ma? Acceleration is 0. Force is not 0, resultant force is not 0. 30 newtons upward, 20 newtons downward, resultant is 10 newtons upward, equal to m times a, m is 2 kg and acceleration is 0 because he is holding it at rest. What happened to Newton's second law? Direction of the force is not upward. Please apply upward force. Why you are applying force in different directions? Okay. So, the force applied by him on this pipe bag system has a vertical component and also a horizontal component. That is what you want to say. Okay. Now, if there is a horizontal component, earth is not applying any horizontal component, and if he is applying a horizontal force, once again why it is not accelerating in the horizontal direction? Why it is not accelerating in horizontal direction when there is a resultant force in the horizontal direction? So, if you want to save Newton's law at least in horizontal direction, believe that the force applied was only in vertical direction, although the Newton's law is still in danger in vertical direction, but putting double danger also in horizontal direction, there is a problem with F equal to m a, at least we can avoid that part. So, what happened?
Sir, this is a case of actually considering the static equilibrium.
Correct?
For that, what will matter is not only the force balance, but the line of action of force, which will change, like it will cause a moment, and that is what is causing the as you increase the distance of the bag from the support, it's causing the moment.
It is causing the moment, yeah.
So to counter that,
To counter that, require more force. Once it is more force, the resultant is not 0. Resultant force is not 0. If the resultant force is not 0, it will not remain in translational equilibrium. Some of you are from mechanical engineering department, I believe. Who are from mechanical engineering departments? Okay, so some 5-6 people. Okay. So, yes, for rotational equilibrium, the total moment or total torque should be 0, and if I am increasing that distance, the gravity moment of gravitational force I am increasing, all right. So, it has to be counterbalanced, but independently there is also a translational equilibrium, right, and for translational equilibrium the total force, net total force is 0, correct. If you have a beam here or if this roof is here and walls are here, then walls are exerting upward force and the weight of it being balanced by this N1 and this N2 and so on. Okay. But if lot of people are walking on the roof, so the center of mass is shifted and the moments are produced, this N1 and N2 will adjust their values, okay, to balance that extra moment, but N1 plus N2 will always be equal to the weight of this slab. So, the translational equilibrium also has to be ensured, and for that the resultant force must be 0. So, he cannot increase the force anymore from 20, he cannot make it 21. The translational equilibrium will be endangered. So, if you answer, please Suchet. So, if you analyze simpler situations like these, okay, then you sharpen your skills to deal with larger systems. Okay. So, I leave it as a homework. When you work it out, you can write to me your answer at hcverma@iitk.ac.in. Okay. All right. So, let us move to some more fun activities. Now, here is a coil and at the end of the coil I have put 2 LEDs, right. There are some, I think 1000 turns or so, is all wound in our lab. And then here is a magnet, and I am putting the magnet here, and then if I shake it, what is happening? So, why the LED is blinking? There is no battery here. Changing magnetic field. And how does the magnetic field change? Because the magnet is, magnet is being moved. So, at any given point, the magnet is changing its distance, changing its magnetic field, and that changing magnetic field is creating induced EMF. Good. So, that is why the red one is glowing. Why the other one is not glowing? There are 2 LEDs connected, only one is glowing. The magnetic field does not change for the second one, it only changes for the first one. Direction, but I am going from this side to that side and that side to this side. Okay, let us see. Huh? So, what happened now, and why that blue one does not glow when I do it slowly, and why suddenly if I do it fast both of them start glowing? More voltage. Blue needs more voltage, therefore, we have to give large velocities. Which one is glowing? Which one is glowing? Which one is glowing easily? And now, so to glow red I need more velocity, and for glowing this blue I need small velocity only. So, which one needs more voltage? Which one need more voltage?
Blue needs more energy.
That's right. That's right. You are right. This red can glow at very low voltages as compared to that one needed for the blue one.
Magnet distance.
I am going from this end to that end. The magnet is hitting my thumb and hitting my finger. I cannot.
It is about north and south.
It is about.
North and south. You just shifted that end of the magnet.
Okay, work out. How many are from electrical engineering? Electrical, work it out. What happens? Your observation is very correct. What I am doing is, in one case, this red is glowing at low velocities, and I need higher velocities for the 2. And now I am inverting this magnet. I am inverting this magnet, and when I invert the magnet, the blue glows easily, and for red I have to increase the velocity. Okay. Now, take it as a project. Understand it and do a theory of it. I have not done it, and therefore, if you do it, please write to me. What happens by inverting the polarity? Anyway, it is going from this side to that side, comes out, then it goes from that side to this side. So, the only difference should be in principle, that in one case, if red glows while going, blue glows while coming back, it should be inverted if I invert the polarity. Okay. So, by inverting the when north is coming out, when south is coming out, when north is going in, and what is the velocity here, what is the velocity there, you can see this experiment as much as you wish, and then work out a theory. If you can work out a theory of it, put your equations and predict that yes, in this case this will happen, in that case that will happen, that will be very nice. Okay, good. Fine. By the way, how this induced EMF is produced when the magnetic field changes. If I do not have the coil, I have the magnet and I am shaking the magnet. Is there any induced EMF? But the magnetic field is changing, so it should do something. If the magnetic field is changing, it should do something. Is it producing something? Is it producing something now? It is producing. Okay. It is producing electric field, and it produces electric field irrespective of whether you have put the coil or not. Right. A changing magnetic field produces electric field. Right. Curl, what is that? Curl of E is minus that everyone remembers. Curl of E is minus dB dt, that everyone remembers. Okay. So, if there is a dB dt, is there a dB dt? Because the magnet is changing its position, the magnetic field at any point is changing its value, right. So, if the dB dt is there, there must be an E, so that curl of E is equal to dB dt minus dB dt. So, it is producing electric field. When the coil is there in that vicinity, this electric field drives the electrons. This electric field drives the electrons, and that is why we say that an EMF is induced, because I have a coil, I have a circuit and I am producing a current. So, I am saying that okay, there is an EMF, but that EMF is nothing but the field which is created by this magnet, changing magnet, moving magnet, and since the coil is there, this electric field is exerting forces on the free electrons, and hence there is a current, hence there is a induced EMF. So, the basic thing is that it produces electric field, not that it produces induced EMF, right. Okay. He is Amit Kumar Bajpayee, and he is from a local village adjacent to IIT Kanpur, and in my team I have all people working with me who come from these local villages only. Okay, so these people maintain my laboratory, these people assemble things, these people suggest me, okay, this is the kind of audience, you take this experiment there. So, that is it. Yeah, next. Okay. So, related to this electromagnetic induction only, what I have is this again a coil. This is a coil here inside, few thousand turns are there, and then inside this we have put, can you recognize what is this? Very commonly available material, there is large number of thousands of them in this campus. Cycle spokes. Okay, these are all cycle spokes that we have put here, right. So, and then this I will be putting into the power supply, normal power, AC power. And this is an aluminum ring. Okay, this is made of aluminum. So, we put it here and give the power. Okay, can you see what is this ring doing, aluminum ring doing? Right, where is the ring? So, it is here now. When I give the power, it jumps and then it stays here, all right. So, first, why does it jump? Why should it jump? magnetic field, changing magnetic field. Why is the magnetic field changing? Where is the magnetic field coming from? From
Coil motors.
where is motor? There is no motor here. In motor, when you give power, things rotate. Okay, that's called motor. When you give current, then it rotates. That's called motor. But here nothing is rotating as such. This is just a coil. Several thousand turns of that, and then finally the two ends are going into that 220 volt power supply. So, where is the magnetic field coming from? Coming from the current. Magnetic field is exclusively created by currents. Is there any other source of magnetic field? Currents produce magnetic field. Is that okay? Currents, any current anywhere will produce a magnetic field. That is right. Is there any other source apart from the current to produce magnetic field? Permanent magnets, yeah, okay. Earth, okay, Earth produces magnetic field, yes. But Earth produces magnetic field because fill in the blank. Earth produces magnetic field because someone had put a big magnet inside the Earth. Because of the central core. So, what happens there? What happens there? Huh? It has molten iron, yes. So, someone has magnetized that molten iron by rubbing with a strong magnet, because normal iron piece does not produce magnetic field, it is rotating. So, so if I take something anything and rotate, will it produce magnetic moment? Charges, right, charges are there. Okay. At that high temperature, the electrons are pushed out, and then you have charges, positive and negative charges, and these charges rotate, and when the charges rotate, it becomes current. That is the meaning of current, motion of charge. All right. So, you have current, electric current inside the earth, and it is that electric current which is producing Earth's magnetic field. So, Earth's magnetic field is coming from the electric currents. Permanent magnets, are there currents? Permanent magnets. What is the difference between permanent magnet and unmagnetized nail? All right. So, what is there in the domain? What is there in the domain? Small magnets. Okay. These magnets are made of which kind of atoms? Wait. Those are properties. I am talking material wise. People from material science department, material engineering. I am talking of materials. So, if I have an iron piece, we say that each small part is like a magnet with arbitrary orientations, and then when I rub or when I put it in a magnetic field, then they get oriented and they form domain and this and that. So, what is that tiny elementary magnetic particle in the nail, and how does it differ from a normal iron particle or normal iron atom? Iron atom has how many protons? Iron atom 26 protons, correct, 26 protons, and some 32 electron or 30 electrons, neutrons, 30 neutrons. The total is 56. All right. So, this iron atom and the tiny magnet you are talking of, The nail is a combination of tiny magnets. So, in that tiny magnets, is there something else other than this iron atom?
They have interaction. They are all aligned in same direction.
So, essentially there is no special substance, okay? There is no special material, it is all iron. All those iron atoms have the same structure, 26 protons, then 30 or 31 neutrons, 26 electrons, and this is combination of these iron atoms. Then there is interaction with them, and this whole iron atom is oriented. All these iron atoms in so called domain, they orient in the same direction. So, if the electrons, if the outer electron is moving seen from this side anticlockwise, then in the domain other iron atoms, those electrons are also moving in anticlockwise direction. That is the meaning of domain getting aligned. There is no extra magnetic material inside that nail. Okay? There is no extra material, it is all the same iron atoms, only atoms. It is only that they are oriented in a certain fashion, they are grouped in a certain fashion and all that. So, from where that the north south pole come in? The nail does not produce magnetic field. Once I put this, when I rub this nail with a magnet, then it starts producing magnetic field. From where this magnetic field is coming? It is again coming from those currents, the electrons which are in motion in atoms. All right. When I magnetize something, what I do is each atom is now oriented parallel to each other in a certain region which we call domain, and therefore, the magnetic field of each tiny loop of that electron going around the nucleus, they are now adding because they are parallel to each other, and therefore, they produce sizable magnetic field. So, even the permanent magnets, when they are producing magnetic field, it is because of the currents, it is because of those electronic motions. The atomic electrons are going around the nucleus, and this current, when the charge goes in a path, when the charge moves, it makes a current, and it is this current which is producing magnetic field, right. So, permanent magnet, Earth's magnetic field, they are all result of currents. Is there any other source which can produce, apart from the current, which can produce magnetic field? Change of electric field. You also have curl of B equal to mu naught epsilon naught dE dt, right, mu naught J plus. So, mu naught J is the direct magnetic field because of the current. What is J? In mu naught J, curl of B equal to mu naught J. What is that J? Current density. So, the current is going. So, the magnetic field because of the current is contained in that mu naught J. But then even if the J is not there, even if there is no current, even if J is 0, you still have curl of B equal to that mu naught epsilon naught dE dt. So, changing electric field will produce magnetic field, just like changing magnetic field produces electric field, right. This was in fact the contribution of Maxwell. Changing electric field also produces magnetic field. This is the contribution of Maxwell, and just with this contribution, all the laws, Gauss's law and everything becomes Maxwell's equations. Curl of B is mu naught J was known prior to Maxwell, right, and this extra term epsilon naught mu naught dE dt, that was added by the Maxwell, but the whole equation becomes Maxwell's fourth law. Not only that, that previous one, curl of E equal to minus dB dt, Maxwell had done nothing to it. Maxwell had done nothing to it. It is a Faraday's law, right? This is Faraday's law. Curl of E is minus dB dt. If you change magnetic field, then electric field is produced, but that becomes Maxwell's third law. Then divergence of magnetic field is 0. Maxwell did nothing to it, but it becomes Maxwell's second law. And divergence of electric field is divergence of electric field is rho upon epsilon naught, right. That this is Gauss's law, that also becomes Maxwell's law, Maxwell's first law. So, all the 4 equations are called Maxwell's 4 equations. Okay, so coming back here, this changing magnetic field produces, why the magnetic field is changing? Because we are giving AC, right, that power which is coming 220 volt AC. So, that is why the current is changing its magnitude and direction in the coil, in the main coil, and the magnetic field is changing, and therefore, an electric field is produced, and therefore, the electrons of the aluminum ring start moving, and there is a current in the aluminum ring, and there is a current in the coil, right, this original coil, this coil here, this coil, there is a current here, there is a current here. Okay. And the directions of current are such that they repel. This is Lenz's law. What is Lenz's law? What is Lenz's law?
It will always cause the opposite to the action.
If the magnetic field changes, if it does not change, Lenz's law has nothing to come into picture. But if the magnetic field changes, and then you have certain circuit out there, the direction of current in the circuit will be such that it will oppose the change in the magnetic field. If the magnetic field is increasing, it will produce current in a direction to give opposite magnetic field, so that it reduces. If the magnetic field is decreasing, it will produce current in your circuit in such a way that it adds to the original magnetic field. It opposes the reduction, it opposes the enhancement, right. So, that is Lenz's law. So, when I switch the power on, the current in the original coil was 0. When I put the switch on, suddenly it increases, and therefore, the magnetic field is increases, right. So, the magnetic field has to be reduced, okay, and therefore, the current in the aluminum ring is opposite to the current in the coil, and opposite currents repel, and therefore, it jumps, right. The sequence of the argument goes like this. Originally, when the switch was not on, everything was 0, current was 0, magnetic field was 0, no current anywhere. Now, you put on the switch at t equal to 0, and the current is building up in the coil. Okay. So, current is increasing from 0 to some value. So, if the current is increasing, magnetic field is increasing. So, the induced current in the aluminum should oppose that increase, and therefore, the current in the ring should be in opposite direction, opposite to the direction of the current in the coil, and if the currents are opposite to each other in direction, they repel. So, it jumps. So, Lenz's law is fine. But now, the problem is initial jump is fine, but what happens afterwards? It is an AC. This current in the main coil will not keep on increasing after reaching the peak value. How much is the peak voltage value here in this socket? 220 volts. Really? our tube lights will be very dim. If it is 220 volts peak value, 220 into root 2, 220 is the RMS value. Okay, 220 is the RMS value, the peak value is root 2 times that. So, once it reaches that peak value, after that it has to decrease, and if the current decreases, the current is also sinusoidal. If the voltage is sinusoidal, current is also sinusoidal. So, the current decreases, and if the current in the main coil decreases, the magnetic field will decrease, and therefore, the force the current in the aluminum ring should be in the same direction as the current in the main coil in that half cycle. Okay. So, half the time the two currents are parallel to each other, and half the time they are anti-parallel, they are opposite. So, that means half the time the coil is attracting this ring down, and only half the time it is repelling. So, why it stays at a certain height? Because the gravity is always there, gravity is not oscillating, it is mg downward. So, that repulsive force should always be there to balance that. But if half the time there is repulsion, half the time there is attraction, the average is 0, average magnetic field, magnetic force is 0. So, why it stays there? Initial jump is all right, initial jump there is no problem about that. Now it is staying at certain height. So, what is balancing the weight? Okay. So, homework number 3, homework number 3, work it out. Why it is staying at rest, what is balancing gravity. Okay. In the same apparatus, we can also see more phenomena. This is red LED glowing. Okay. This LED was at the end of this copper coil. So, if there is a current, that current also goes through the LED, and therefore, the LED glows, that is fine, but this copper ring had jumped and stayed at a particular height. Why this did not jump? The LED is glowing, that shows that yes, there is an induced current, right. The aluminum ring jumped, that showed that yes, there is a induced current. Because of the induced current, there is anti-parallel. So, initially it was jump, and then there is a suspense why it stayed there, but initial jump was fine. Why did this not jump initially? When I switch the power on in a similar fashion, the current is induced, okay, but aluminum ring jumps and this does not jump. Okay, it does not jump. So, what happened to Lenz's law? So, all great scientists are being challenged, starting from Newton. The Lenz law is not working here, it is not jumping when I switch the power on. Okay. All right. If I take this coil up, what is happening? Can you see what is happening? If when I take this coil up, and somewhere here barely you can see a red spot, Are you able to see the red spot? So, up to this height, the intensity decreases, and at this height it becomes barely visible, almost invisible, right. I have another LED, similar structure of coil, same number of turns, but the LED is now blue LED. Okay. So, the blue LED is here, and if I take it up, you see here itself the intensity has gone almost 0. Can you see the blue thing? Can you see the blue thing now? No. So, it is already gone. Okay. If I bring it from top, somewhere here it starts, somewhere here it starts showing up, whereas for the red one, from here itself. So, it supports that statement that you made, that red needs less voltage and blue needs more voltage, and that also shows that the induced electric field here is large, and as you go up, the induced field decreases. Why does it decrease? Why should it decrease as you go up? Yes. At that base of, at the platform of that coil, the induced current was large, the LED was glowing bright, and as I am taking it up, the LED intensity is going down. So, that means the induced EMF or induced electric field, the magnitude is decreasing as you go up. Why? Why should it? More leakage. It is all related to your dB dt. Curl of E is minus dB dt. So, if B is strong, dB dt is also strong. As you go up, because of the magnetic field is going out, then the B is small and dB dt is also small, right. Okay. Now, the last one. Now, these are two plastic sheets, very special plastic sheets. Good, my name is written on your notebook. Can you read my name here?
Yes.
Yes. I am putting both the sheets together and then putting it on the notebook. On the notebook it is written, some words are written H.C. Verma, and through these two sheets she is able to read the name, correct. You have also written something. Once again I am putting the two sheets together and putting it on your notebook. Can you read what is written on your notebook? Absolutely no. But your friend was able to read.
You twisted him.
I twisted. Okay. So, these are the two sheets. I am putting them together and putting it here. Can you read?
Yes.
Read. I am taking two sheets, putting it here and then putting it here. Are you able to read?
No.
No. So, this side people can read and this side people cannot read. So, what are these two sheets and what am I doing? What am I doing? Why you are not able to read? You are not able to read the same two sheets.
Just
And
flip the one over other.
yeah, and flip the
Flip one over other.
like this. Okay.
Is that the same?
Okay.
Or you can
Look at this
or you can
and look at this.
rotate.
Rotate. Okay, good. So, it is a rotation which is making the trick. Okay. If I rotate it this way, almost everyone should be able to see that it looks very clean as compared to this orientation. It becomes black. So, the light is not crossing through, but in this orientation the light is crossing through. So, what are these things called? Polarizers. Very good. Bulb? अच्छा bulb नहीं रहने दो, चलो छोड़. नहीं ये तो लास्ट का हाँ कर सकते हैं, यहाँ पर कर सकते हैं, बट आप बल्ब जलाओ पहले, इससे रिफ्लेक्ट करेगा क्या ज़मीन से? यस इट इज़ डूइंग इट्स जॉब. इसको कहीं पे आप रख दो. Look at the image of the bulb in the floor, okay, through this, and then rotate, and then tell what you see.
Yeah, like this I'm unable to say it, but like this I am.
Okay. So, if you look at the image of the bulb in this floor, okay, through this polarizer sheet, and if you rotate the sheet, you will see that the intensity is changing. I am using only one polarizer. At this orientation almost gone, nothing is being seen, and at this orientation lot of things are seen. Want to try? You can come here and try. Look at this image which is here in under this floor. It's not visible, and now it is visible. So, intensity is changing. So, why is that? Polarization by reflection. Okay. Now, one more volunteer can come, and okay. One more. Someone want to experience? Come forward. Come forward. Yeah. Okay. Good. Now, these people say that if I look from one orientation, the intensity of what you have to look, not the bulb, the image of the bulb. So, these people say that from certain orientation of this polarizer, you do not see the intensity, and it is almost 0, whereas if you rotate it, you start seeing it and the intensity increases. Verify what they have said. Does the image vanish? It does not vanish. Come on.
So you have changed the sheet.
I have not changed the sheet.
Utilizing
From all orientation it is seen. It is not vanishing. You want to verify which of these two people are telling lie? Who want to verify? You want to verify? No? You want to verify? You will check. Okay. Okay. यहीं से कर लो. उतनी दूर क्यों जा रहे हो?
दिखाई तो दे रहा है.
दिखाई दे रहा है.
इंटेंसिटी कम हो ज्यादा.
इंटेंसिटी कम हो ज्यादा हो, लेकिन दिखाई तो दे रहा है. ऐसा कोई पोजीशन है कि बिल्कुल नहीं दिखाई दे, धीरे 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 धीरे,
हाँ
है ना? है ना?
ये वाला.
ये इसमें बिल्कुल दिखाई नहीं दे रहा है द इमेज, राइट? देखो भाई, ये आपके फेवर में इन्होंने बताया है, लेकिन आपके फेवर में नहीं बताया है. आप या प्लीज कम.
You already changed the distance. Distance from where and
Yeah. Does the intensity vanish?
no.
It does not vanish. Is it increasing or decreasing sufficiently, significantly?
It is not.
Not.
No.
Almost the same intensity. So, what is happening?
But even the distance is changing.
The distance is important. But why is the distance important? The angle of incidence. How much it will polarize? How much it will polarize depends on the angle of incidence. Okay? and at a certain angle of incidence, it becomes perfectly polarized, and then if you put your polarizer in right orientation, it can vanish. And what is that angle called? There is a name for that angle, Brewster's angle, and there is an equation to calculate that Brewster's angle. Calculate, this is measurement. To calculate, there is a equation, tan inverse mu 1 by mu 2, right. So, one is air and other is the other medium, and then the refractive index of that medium with respect to air is mu. Tan inverse mu is the Brewster's angle. So, I have measured I have obtained that Brewster's angle, right, from certain places. There is a certain angle of incidence, and I could see that the intensity becomes 0, it is perfectly polarized. So, I have gotten the Brewster's angle, and it is equal to tan inverse of mu. So, I have gotten mu, I have gotten refractive index of what? Of the floor. Yeah, so where is the second medium? One is the air and the other medium is
Floor.
But the floor, does cement has refractive index? Is light going into the floor, and sin I by sin r equal to mu. So, is light penetrating this cemented floor and going inside and bending towards the normal, and I can talk about refractive index. Work out. Please work out. What is the meaning of refractive index of a cemented floor? Okay, so now this is the last one. And after that, if your convener does not come, I do not know what to do. Because up to 4 o'clock, I am in the control, 4 is already 4. Okay. What color do you see? Color. And what color is this? So, if I put all the 3 together, then what color it appears?
Same as the sheet.
Right? Same as the sheet. And now see the magic. Is there a color? Which color is this? Which color is this? Huh? Now it is?
Kind of blue, sir.
Kind of blue. Blue. You can also see blue. What color is this?
Blue.
This was not blue. This was not blue. This was not blue. When I put all the 3 together, it becomes blue. Okay. So, what is happening? What is happening? And what color is this? And I put it here.
Oh, it became red. Red, purple, violet, something.
Guess what is happening? How the colors are appearing? There is no prism to split your white light into different colors. These are 2 polarizers. Right? Can you see the color? And if I rotate my polarizer 90 degree, see what happens. Are you able to see anything?
No.
And now I put this thing, it becomes transparent. And what is the color? Okay. Nothing comes out, it's black, black, black. I put it here, still black, black, black. But if I make it at 45 degrees, you see the nice green color. Can you see the nice green color? No color here. This is green and no color here. And if I rotate it so that light does come out, then you see the color. What is this property? Yes. What is this property? Okay, let me tell. This is glass slide used in biology classes. On that glass slide, we have put cellophane tape. The tape which you use to put across your envelope. That same tape, a layer of tape is there. In one of the slides is one layer, other slide 2 layers, and so on. Okay. So that's the structure. That is the structure. And empty slide doesn't show up any of the colors. See the color here. What is this color? Yellowish pink, right? And at 90 degrees it shows me greenish. Okay. So this whole thing is coming because of that cellophane tape. Cellophane tape put between two polarizers in any orientation, crossed or parallel, shows up color, provided that cellophane tape is at some angle, preferably 90 degrees, 45 degrees. Why is that coming? First thing, it was nice to see, right? So good colors just by rotation and all those things. It was a pleasant exercise. Okay. And then the science behind it is that cellophane tape is a very good optical material. It shows birefringence. Okay. It shows birefringence. There are two refractive indices of cellophane tape. Normally a transparent material has one refractive index, but here there are two refractive indices, and there are several materials which are birefringent. So length of the tape and width of the tape, they are not similar. If light is going perpendicular to the tape, when I am seeing, the light is coming perpendicular to the tape. So the electric field can be in any orientation in the perpendicular plane. So if the electric field happens to be parallel to the length, there is one refractive index, the speed of light is different. And if the electric field happens to be along the width, the speed of light is different. So that is how there are two refractive indices of this tape. Okay. And since the refractive indices are different, when they cross the thickness of the tape, so during that there is a phase difference, and that phase difference is different for the two kinds of electric field, one parallel to the length and one parallel to the width. And this phase difference, then the other polarizer is at work. So it cuts a certain electric field and allows certain electric field. So different wavelengths also have different refractive indices, dispersion. Okay. So for different wavelengths, the phase difference produced is also different, and therefore when I put it at 45 degrees, one component of the electric field is along the this length, and one is along the width. You have to divide in two components, right? Because first polarizer is already, it has produced an electric field in some direction, first polarizer. And then your tape is at 45 degrees. So along and perpendicular, you have two components, and the two components are coming out with certain phase difference. It becomes elliptically polarized, but different colors are having different kinds of ellipses, and the next polarizer is cutting according to its own axis. So some of the colors are cut more, some of the colors are cut less, and that is how you see this colored appearance. So this cellophane tape is not just a simple material, it is very, very good optical materials. Okay. All right. So I was given 1 hour, so I have consumed that 1 hour. So, all the best. You are starting your teacher's profession, right? Teaching profession. It's a wonderful profession, I tell you. I have spent 38 hours in formal teaching, 38 years of formal teaching, and after that I am doing a lot of informal teaching like this session. It's a wonderful profession, very good profession. If you start enjoying this, all right, you will not have time to make complaints to your principals and AICT and others and others and others, even if you are exploited. It's such a wonderful profession. But for that, yes, you have to, you should be able to see through all the things which are there, what engineering is being is governing that phenomena. If you are able to see that in the world, what kind of how the science is operating, how the engineering is done, then it's a really very good profession, very nice profession. I must congratulate you that you have chosen this one and you have not gone to some other companies and this and that. All right, thank you and all the best. Chalo.